where does ZTF fit in? ZTF, which is the successor to IPTF, which is Improved Palomar Transient Facility, which it was the successor to PTF, Palomar Transient Facility. Long line of telescopes, or long line of cameras operating on the P48 at Palomar Observatory. The P48 telescope, can't remember exactly when it was built, but yes, that's what we all depend on for our data. So what was needed was a robust high bandwidth data processing system and archive capable of holding multiple petabytes of data, which has been produced by ZTF. So how does the data get to Ipac? It's actually more than just the internet. So what we use is a system called HPREN, which is a microwave connection from Palomar Observatory to University of San Diego, specifically the San Diego Supercomputing Center. And then from the San Diego Supercomputing Center, we have a gigabit connection to Caltech and specifically to the Ipac Data Center, which is located in Morris Row building. I think it might be Morris Row Memorial Building, I'm not sure. Yeah, but we have just over 100 employees on the Caltech campus, but the ZTF team is pretty small. There are only 3 of us working on the data system. It used to be larger, but since development has fallen off, and yeah, pretty stable project at this point. So the ZTF Ipac pipelines, currently there are 13 internal pipelines in use that have the ultimate goal of producing real-time alerts on the order of 10 minutes. Usually it's about 10, 12. Sometimes it can go up to 50 minutes depending on the field being observed or any number of other issues with or issues, I guess, not necessarily actual issues. And then those are published via Kafka, which is a distribution system, which is easily queryable by any number of brokers. An example being Fritz. Also, there's the partnership broker, which will be talked about later. And then we also are directed to provide products in an easily queryable archive, which is distributed via URSA, which I mentioned earlier. Right now, I just checked this morning, there are 4.2 petabytes of ZTF data on URSA. It is the largest project supported by URSA. Definitely in the era of big data here. We have public data releases every 2 months. So for example, we just had a data release on the 7th of July that covered data from, I believe, May 5th to July 6th. No, from, my apologies. So it's delayed 2 months. So it would have been March 5th to May 5th or something like that. So the next release, which is in September, will cover May to July. But that's just for the public program. For collaboration in Caltech, I don't know why I put observatories there, my apologies. There is an 18-month proprietary period for that data. So if you are not part of the collaboration or part of Caltech, that data will be released for you 18 months after observations are done. So a little bit more about the specifics of our data system. We have 66 worker nodes running CentOS. Most of them have 32 cores and 126 gigabytes of RAM. During the night, these are fairly well populated, probably about 70 or 80% usage, or even more on more intensive nights. And we also have 2 special nodes that have 40 cores of RAM, or 40 cores and 756 gigabytes of RAM for those larger pipelines. Like I said, there are 13 internal pipelines, but really, you only really interact with one. All you scientists, when you're querying for things from Fritz, or you're querying for things from Ample or something, your data is likely coming from what you might call the Ipac pipeline, which is really just one of the many pipelines that exist in our system. But that's mostly the real-time alerts pipeline. And I would like to establish something. I just want to go over the layout of how ZTF works, the camera itself, because there's been a little bit of confusion, at least here in the room, as we've been going on day to day. So ZTF itself has 16 CCDs, and then within those CCDs, there are 4 quadrants. And at Ipac, what we do is we process them quadrant by quadrant. So when we're reading in data, what we do is we so right here, after we have ingested the data, we split so we receive 16 different files from the mountain. So 1 for each CCD. And then since they're FITS files, we just break them down by HDU into the quadrants. And then those are sent into our nodes to be processed by whatever pipeline they need to be processed by. So just to clarify, the nodes are not necessarily, or the quadrants are not necessarily ordered in a intuitive way, but it is logical based on different processing and how the robotic telescope operator ROS works. So yes, if anyone is having trouble with understanding why you have 64 different sort of things per exposure, that is why, because we process per quadrants. So what exactly are the input and output data for a given night? So at the beginning of observations, the calibration pipelines run, and we receive 20 bias exposures, which reveals the inherent bias of the CCD quadrants. A bias exposure is something that's taken with the shutter closed and no lights on, and it's essentially just bare what the CCD sees if there's no photons hitting the camera. And with these 20 bias exposures, we stack them and we do a little bit of analysis on it, and we create a bias calibrator, which we can then subtract out of the science images. And then similarly, we have 20 flat exposures per filter, except for the eye filter. That one requires 21 for some reason. That's just historical, and probably it improves quality somewhat. And this helps eliminate filter-dependent imperfections, namely dust. There's a lot of dust in the telescope, surprisingly. And with those 20 flat exposures, we create a flat calibrated image for each filter. So with that, going into the science and real-time pipeline products, what we do is we take those flat and bias exposures and we'll subtract them out from the raw images and create science images. We also calibrate these with masks. There are a few different types of masks available. Specifically, there's source masks, and there's bad pixel masks, and there's a number of other things that we do. And then another, the thing which triggers the alerts, the Kafka delivery, are the existence of difference images. So I'll go over specifically how the pipeline decides whether or not it can create a difference image in a little bit. But what happens is, once we have a science image, if there is an existing reference image, which is a co-added stack of a few different science images, we can say, is there anything different in this science images than what we previously see? And if there is, we can subtract it and create a difference image, and we'll create an alert on any source that looks different from what it previously has looked like, and we'll send that out. Some other different types of data that we produce and provide to the community are, of course, the real-time alerts, which we provide image cutouts for, and a number of other things packaged in the Avro format. And then we also have moving object information. There's Z streaks, which I'll talk about a little bit later, and also Z mode. So Z streaks tracks fast moving objects, and Z mode will track one object over many different images throughout the night. It's good for tracking slow moving or far away asteroids, comets, et cetera, et cetera. So here's a sort of high level diagram of the Ipac pipeline. So as you can see, it goes from P48, which is the telescope, camera imaging and packaging software, RAWs, to the San Diego Supercomputing Center, and then we ingest that over the internet and then split it, as I talked about. And then we decide, okay, so if this is a calibration exposure, we're going to ingest that into our calibration pipeline, and then that will be set for the night per filter, et cetera, et cetera. If it's a raw image for an object exposure or science image, we will register that image and metadata, and then we're going to process that via the real-time pipeline. So the real-time pipeline itself is pretty complex. There's many different steps, but the important thing to note is that there's this pipeline, which I can go over, and then there's if the image meets a certain set of criteria, it will go through this pipeline, which is essentially the second part of the real-time pipeline. So we do all of our calibrations, which are all of these steps here. And then we register some QA metrics, and we register some cataloging metrics. And also we fit the PSFs based on what we previously know, and we try and register sources, compare them to the PS1 catalog, PanSTARRS-1 catalog. That's what we use to find sources. And then we also use source extractor. I think it's called source extractor now. It's not called Extractor anymore. This is a bit of an old image. This is taken from Maskey et al. 2019, which is the big paper on the ZTF data system at Ipac. So we also do a number of other detection steps to see if there's anything of use in the image. So at Ipac, you might see that there's a lot of PSF fitting in here, blah, 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 all these different types of mapping that we do. We do a lot of flagging. So if you're looking at an image and you're looking at the info bits, we set a lot of that here per science exposure and per subtraction. I'll go over exactly how you can see these pieces of data via the internet in a little bit, just a brief overview of that. But just to note that those are not constant over the life of an image. So Palomar will set info bits for a given image, and then we will do it a few different times depending on what products are produced. So the important thing to note is that if a difference image is produced and it is usable, then we will really dig into that image, and we will filter on the type, like what is happening with the sources in that image, and we will do different fitting on it. And as you can see, we run some preliminary machine learning classifiers on it, and we assign a real bogus score. Okay, so as I was saying, we do some preliminary filtering on the images, and we do some filtering on what we actually decide to alert on. So what we see in our difference images may or may not qualify as good enough to send out an alert. At times when things go very wrong, say very recently what happened was a different filter was put on the telescope. So our data system says the sky looks different than what I've ever seen it as. I'm going to send 2 million alerts in one night, which is very bad because it clogs everything up. It produces tons and tons of bad data. And the night is pretty much unusable at that point. So that's just something that's happened in the past. We're working on ways to make sure that doesn't happen again. But that's part of the idea that we fit PSFs compared to what historically we have known. It's not a ground up every single night type of thing. Oh, camera. Yes, I see. Okay. So like I was talking about, so that's all in here. That's this little red box pretty much. And then at the end of every night, what we do is we take the good images and we say, are any of these fields that we see field? Okay, so really it's a combination of field, filter, and RCID. Just a reminder, RCID are these little tiny quadrants. So there are 64 of them on the camera. And we say, do we have a historical reference image for this specific field, filter, and reference or RCID combination? And if we don't, then we say, okay, last night did we observe enough that we can co-add a bunch of different images and say, this is a historically constant view of the sky that we will then record and use to decide if we want to create different images in the future for that field, filter, and RCID combination. Okay, so that's the creation of reference images, which the reference images are incredibly important because they essentially allow us to create these alerts. So if you're ever requesting observations on ZTF and you're like, I want to observe this new field, just know you probably won't get alerts on it right away because we need to construct a history for what that field looks like in order to tell you if it's different in the future. So the real-time pipeline feeds into our Kafka alert system, which then goes to brokers. Brokers ingest our alerts by the thousands every single night. And there are a number of different brokers. I think Guy is going to talk about Fritz and Sky Portal later. There are a number of alert brokers who are using ZTF as a test bed for LSST alerts. LSST is going to produce about 10 times more alerts than ZTF does every single night because it's a lot deeper than what ZTF can do. But even though our footprint is larger. Anyway, so that's just for stars and stuff. So Frank Maskey, the one of the main architects of the pipeline, in combination with another developer, Russ Leher, developed Z mode, which is a really complex and very impressive pipeline to track moving objects within the solar system, like I mentioned earlier. And it's really amazing. I think there's a paper on it if anyone wants to look at it. That's not really what we're talking about here because this is multi-messenger astrophysics. Okay, so I'm going to stop sharing this and we are going to go to a different, how much time do I have? Okay. I'm going to go to a different thing over here. So I have a number of links which I can provide at, if anyone would like to see. So this is the main paper. It really contains a lot more information than what I could provide you. There are 30 pages, as you can see. And then we have even more. There's a 123-page explanatory supplement, which goes even in more depth. And really, if you're looking at specific images, which I don't know if a lot of you are going to do, but if you want to construct your own pipeline for ZTF, you're definitely going to need to understand a lot of this. Specifically, the quality flags which we set are deeply explained in this. So there are 26 bits for quality that we go through and we look at every single image and we say, is this good or bad? Is this good or bad? Is this good or bad? And then we use those 26 bits to define what type of goodness or badness a given image might have. And that's all explained in here. Yes, but also we do public data releases every 2 months, as I said, and we release a comprehensive explanation document for each release, and we provide coverage maps for what the release covers, and we provide certain statistics if anyone is curious. The data scientists out there are probably drooling right now, but yes, the important thing to know related to the data releases is really how to get to the images that you want. So Ursa is really helpful in that sense because it has a number of products that you can query via APIs, or you can just do a catalog source. So if you know what source ID you want, or I think it's object ID, you can search them here. As you can see, there are many billions objects. I'm gonna try that. Or you can go directly to an image and you can either enter an object name. This is what Ned does. Ned will try and match a given name of an object, say a galaxy or a star or something. And then it will provide you with an image in the ZTF catalog related to that. Or you can just do RANDEC, either way. That's an easy way to see images, and yeah, I won't. But the GUI on Ursa is actually really nice. There's a lot of things that you can do there. But I do encourage you to look through the data release document, because it really shows exactly what we give with each release. Because while I did spend a lot of time talking about what we do release, there are also all of these types of catalogs and exactly what we do to the image. We provide that with each data release. So it is important to understand that all of this is publicly available. And if you question what we're doing, you can go and look at it. But also this is important because there are groups working on doing their own calibrations and really trying to improve upon what we do. It takes a little bit more time, so I'm not really sure how feasible it is to implement in the real-time pipeline, but they're doing really, really great work and trying to do some better cuts on all of this. And we also have the force photometry service, which some of you I know are familiar with. It's sort of, it's not our primary service, so you can only submit 100 requests at a time and wait for those to finish and then submit 100 more. There's also the Ursa light curve service, which you can see here, and that's pretty good, but also it's its own beast. And if you have any questions for data access related to Ursa, there's the Ursa help desk that you can query for any problems that you're having. And if you're really curious about a given night and why there is data or why the data is bad, there's skyvision.caltech.edu, which this is just a summary of last night. As you can see, there are a few gaps in observations here. I think that was just weather. As you can see, it constructs an all sky movie using a fisheye lens, and you can see the clouds and everything, even though we do sometimes get decent data if there are clouds blocking things. Okay, I think that's kind of all I had to say. Does anyone have any questions online or in the room?